Hello everyone, welcome to the course Solar Thermal Steam Generation System. In this video, we will take a look at the potential of solar energy, one of the most flexible and fastest growing technologies available. And we will discuss two technologies that extract power from the sun. First one is solar photovoltaics and the second one is solar thermal technologies. Let's first take a look at the photovoltaic panels, otherwise known as solar panels or PV panels. The light emitted from the sun is absorbed by the semiconductor materials in the PV panel. The semiconductor material converts the light energy directly into current of mobile electrons which supplies electrical energy. The panel is connected to an inverter that converts the DC output of the solar panel to AC power and ensures maximum power to the grid. We can characterize the power of the sun by the irradiance. Irradiance means the amount of energy per second incident on the surface of the earth per meter square, and therefore it is expressed in watt per meter square. In order to find the potential of the solar energy, we can integrate the irradiance over a certain amount of time to obtain the irradiation. The total energy potential of the certain PV panel is equal to the product of the irradiation and area of the panel A. The solar irradiation strongly depends upon the angle of the sun with respect to the Earth's surface. The irradiation is highest for locations around the equator and decreases towards the poles. The global data has been made available by the organizations like Solar, GRIS, and NASA for irradiation. The efficiency of the photovoltaic system is equal to the energy output of the system divided by the energy potential of the sun. This includes semiconductor conversion efficiencies and the efficiency of the system components like inverters, batteries, and cables. Most solar models which convert commercially available have an efficiency between 10 to 25% depending upon the technology used. Solar energy is notorious for its low capacity factor. This is because the solar radiation strongly depends upon the time of day and seasonal fluctuations. Especially in countries far from the equator, it has more sunlight available in summer than in winter. Shadow should also be considered. Some trees and buildings can cast shadows that strongly influence the performance of a solar cell. In solar farms, panels can even cast shadows onto each other. This is important when designing a solar farm. In the following example, we want to calculate the energy yield and capacity factor of the Gujarat Solar Park on the top of the west coast in India. The Gujarat Solar Park in India is one of the largest combined solar farm in the world. It consists of 84 large-scale projects that have a combined nominal capacity of 1000 megawatt. The surface area of the farm is 2000 hectares and we will assume a moderate estimation of 15% for the total PV system efficiency. First, we want to determine the annual average energy density. Therefore, we can use this map of India. Here it is shown that the peak receives a high yearly irradiation of 2100 kilowatt hour per meter square. We know that the surface area of the form. However, this should not be confused with the area that absorbs light, otherwise known as active area of the PV surface. We will take an active area of 24%. Ultimately, we will receive a yield of 0.15 times 2100 kilowatt hour per meter square per year times 0.24 times 2000 hectares, which is equal to 1.5 terawatt hour per year. In order to compare with other technologies, we can express the annual generation as energy per total area. The energy density is then 1.5 terawatt hour divided by 2000 hectares, which is equal to 75 kilowatt hour per meter square per year. Finally, we can calculate the capacity factor by dividing the energy yield by the installed capacity multiplied by the hours in a year, and it yields a capacity factor of 0.17. This is all about for PV technologies. Now let's look at some of the solar thermal technology.